Okay, this is still in chapter 5, and one of the things they look at is circular motion. Now, from chapter 3, we introduced circular motion, and we said the acceleration when you're going in a circle was v squared over r, and the direction was towards the center of the circle. And we also added to that is if the velocity was a constant, then we can just use the equation for the average speed. We can say the speed is just the distance around the circumference divided by the time around. Remember, that was the period right there. So now Newton's second law will now be the sum of the forces equals m times v squared over r when you're going in a circle, and the direction is always inward. So now with Newton's second law, we have three ways we can has three forms. If you're not accelerating, the sum of the forces equals 0. If you're accelerating in a straight line, it's equal to ma. If you're going in a circle, it's mv squared over r. And we make sure that we call this one inward positive right there. This one is the acceleration you're moving. So just to look at a simple example, I just have a conical pendulum. It's just swinging around. We looked at the acceleration before. We know the acceleration is towards the center of the circle, which would be that point right there. And so we put our coordinate system toward the center of the circle. And now if we look at the forces on it, we have just our rope forces. There are no extra forces. Don't bring up centrifugal, or any of that. There is none. There's just the forces that we've had. We have the tension and we have the weight, and that's it right there. Now, what do we want to find right here? Well, let's just say we're given the time around and we're given this length. Let's go ahead and find that angle right there. Well, first of all, this r right here, the radius of the circle is that distance right there. And from this triangle, since that's L and that's theta, this is the opposite side, so r is L sine theta. Okay, and so we can also break our t. We have to break it into its components since we have to put our axes this way and this way. So there's your t. There's theta. I just redrew this. So there's the cosine part. I just didn't want to draw it there. And there's the sine part. So now when we look at the sum of the forces inward, the only part we have is the t sine theta. And that equals ma inward, but a inward was v squared over r. So that's the inward force. The forces up and down balance. This is just staying in one plane. T cosine theta minus mg equals 0. So there's my two equations. The easiest way to eliminate the t out of here is move the mg on the other side. And so I have t sine theta equals this, and t cosine theta equals mg, and then just divide the two equations. That way the t's are gone right here. And so all I have is sine theta over cos. I'll leave it as sine over cos rather than putting it as tangent. On this side, the m's cancel. So I just get v squared over gr. So there's that term. Now, since this is moving at a constant speed, we can use our equation for the average speed. And v was 2 pi, the distance around divided by the time. So I'm going to take that and put it into there. But remember, I have to square it. So this v squared becomes 4 pi squared r squared over t squared. 4 pi squared r squared over t squared. I still have the gr. Okay, I can cancel out some r's right here. And then I can remember what r was. Remember, r is L sine theta. We'll put in L sine theta for that r. And now you notice we have a sine theta on both sides. We can cancel these sine thetas. And if we want to solve for the cosine, we'll just flip both sides. So this becomes cosine, and this becomes flipped. It's gt squared over 4 pi squared L. And there's the angle right there. If I wanted to find the tension, you notice I could come up to here, and tension is equal to mg over cos. I could put that in for cos, and I could get the tension if I wanted that. But this is all I wanted to get. Okay, so there's circular motion. The next one will be a little bit more involved.